Okay. Are you feeling better?
Yeah, a lot better.
Like, are you completely fixed or just like?
Yeah, no.
Oh, awesome. So we'll set up a time like later this week.
Yeah.
Now that you're back in commission. All right. So you had a couple of like what 2 or 3 questions for today? 2 questions. Okay. Those went fine, I assume. Not a big deal.
1 for 4, pretty easy. As long as you read.
as long as you read.
Yeah, there was a moment where I was like, oh, it's just an 8-bit pixel.
Yeah.
No.
So at this point, have you pretty much read through all of chapter 1? Ish.
Oh, but all the questions that we had to answer were only through like
Yeah, but
one.
you said-
Yeah. But all the other questions were kind of fluff.
6 or something like that. So
Have
you
you?
watched the class video.
What have you officially read through?
1.10.
1.10.
Oh, is it?
Yeah.
Okay, so you've read through all of that. All right, so let's. We've talked about a bunch of things already at a very, very high level. If you look ahead here, we're going to get into, the ALU, the processor at a lot higher detail, memory at a lot higher detail. So why don't we just jump ahead now and start looking at instructions? That way we can start writing some assembly stuff and that kind of stuff. We have a pretty good high level understanding now of kind of what computers are. Maybe 10%, 20% more than maybe when we walked in the door originally. All right, so then let's move on to chapter 2, which is going to talk about our instruction set, which we already talked about at the high level, so we'll fly through introduction thing here. So we've talked about this idea of an instruction set being the vocabulary commands understood by a given architecture. It's the magic tricks that a CPU knows. That's what the instruction set is. All right, so when you write a computer program, the compiler, well, one of 2 things is happening. Either if we're writing assembly like we will in here, our magic tricks that we can reference are the instruction set that is available for the architecture we're targeting. All right, so for us, we're going to actually be doing something, we're going to be looking at ARM architecture. The book uses something called LEG, which, it's like a ha-ha-ha joke thing. It's not a real architecture. It's like a subset of ARM they call LEG. Get it? All right, so in any case, so it's a cut down version of the ARM architecture, but it'll give us enough of an introduction. And part of the reason for that, and we're going to see it ourselves, is we're going to write, like I mentioned, we're going to write an Android application, or if you really wanted to, you can do iOS. I don't care, but I'll require it in, and I'll suggest an Android since I don't have to worry about whether or not you have a Mac or not. But we're going to write our own assembler for ARM, but it'll be a subset of ARM, which is going to be in the ballpark of LEG. Okay, something like that. But that's going to give us a real clear understanding of how instructions move through the system from memory into cache into the CPU and talking to all sorts of other things. So we're going to get to see those individual pieces. The book comes with I think it's linked somewhere in here. Is it in this chapter or is it at the very end? It has a LEG thing. Yeah, the ARM assembler or ARM simulator that's in alpha that will understand what they've called their LEG commands, the subset of ARM. So they haven't implemented an entire ARM simulator, so they're doing things in terms of the LEG commands, which from our perspective is going to be stuff that's not the specialized magic tricks that perform some very specific task really, really, really fast. Instead, it's going to be kind of the core components of any architecture, which is what we'll focus on. And then, if you end up being an assembly programmer or something like that as for a living, when you're targeting a specific architecture, you will likely be trying to take advantage of the specialized features of that architecture, and that's where you'll get to the more complex magic tricks, which are effectively functions written in hardware or created in hardware or something like that. Okay, I'm gonna hide that. So all right, stored program concept, the idea that instructions and data of many types can be stored in memory as numbers and thus be easy to change. So we're already used to this. We double click on our program, it loads that program into RAM. We kind of have thought about our programs loading into the CPU, kind of one instruction at a time. So the CPU kind of eats from RAM. That's where it feeds off of. And then some things get paused and stuff like this. We want to get down to some actual operations and talk about the various registers. So before we actually get into this, I want to jump in and let's talk about the idea of a hardware register for a little bit. We've talked about it in other classes. We've talked about it at a high level in here, but let's give some meaning to it now. So this is sort of in the conversation about memory, but we have these things called hardware registers, or sometimes they're just called registers. All right, so a register is a really fast and often small, it's called chunk of memory, which lives directly on the CPU. And we're going to call this our fastest memory. When something needs to be really, really, really fast, it goes in a hardware register. Now, a hardware register is something that we interface with using assembly language. Okay? It's where we maybe store our parameters. If you remember back to that Hello World program that we had in Linux or whatever, we kind of loaded 3 or 4 values into some these magical places like EAX, EBX, ECX. These are hardware registers. We put these values into 4 really fast memory locations. That way they're prepared for the CPU to grab them, and that's the quickest place for the CPU to grab stuff like from the fridge. All right, so really, really, really fast access. So if we need something to be quick, we put it there. And the CPU will have the least amount of downtime to grab to load that data. Okay, so we're going to call this our fastest memory. Now, different architectures then have a different set of hardware registers. So when we think about the hardware registers of a particular CPU, in this case, we're thinking about ARM CPUs, we have to consider what are the things provided to us by ARM. Now, the ARM hardware register, I think there's 32 registers in ARM. I'm pretty sure that the book, I think, implements like 11. That's their leg cut down version. But we'll look ahead here in a second and see that. But these guys are going to be of various sizes. So you'll have several 8-bit registers, some 16-bit registers, some 32-bit registers. Some might have 64 or 128-bit registers. So you have crash. So you have several different size registers, and this kind of goes back to thinking about primitive type variables, except this is when it matters. So if you think back to when we talk about, in like Java and C++ and things like that, and why do we have so many primitive types capable of holding whole numbers? We have byte, short, int, long, and that argument goes back to, well, that's, memory used to be really, really expensive, and as an earlier programmer, we had to be very, very careful of how much, if we were storing only a value between 1 and 10, you put it inside of a byte so you're not wasteful of memory. Well, today as a programmer, we don't really think like that very often because we have this abundance of RAM. But under the hood, your compilers are still producing assembly language trying to be as optimal as possible because you only have a fixed number of registers, hardware registers. We can think about these, I like to think about these like a variable built in hardware. So when a CPU has to store a variable, it puts it in a register. And if it's going to hold a value that can fit in 8 bits, you might as well use an 8-bit hardware register. Where generally speaking, we're reliant on compilers to produce our assembly code, right? Because not very often does a modern programmer write direct assembly code. We're going to be doing it in here, because it's fun. Okay? But secondarily, it does exist in industry, especially if you are working with microcontrollers and embedded systems, like fixing dishwashers and stuff like that. Each of these guys has like a little tiny computer in them. And if you work in the engineering side of that, you might be writing tiny programs that run on this little tiny microcomputer that lives inside of a dishwasher or something. And you have to operate at a very bare minimum memory footprint. I think I mentioned this probably the first week of class or something, that you might have a board that has 64K of memory on it. And maybe the next board is 128K of memory. You get twice as much memory, and maybe there's a 6-cent difference between those two boards. Well, from a normal human perspective, it's like, oh, well, 6 cents, I don't have to worry so much about the footprint of my program. Well, yeah, but now you're multiplying that over thousands and thousands and thousands of units. That adds up to real money. So some people's jobs are to create, functional software running on these embedded systems that live inside of various devices, and a lot of times they have to streamline it to get it to fit onto that chip. Okay, so they need to really think about how much memory they have available to them based on the specialized microprocessor that's on that. They probably aren't dealing with an ARM processor. Why is that? If you're somebody who's writing or if you have a little computer, when I say an embedded computer, an embedded system, I'm really talking about a kind of a computer that lives inside of a washing machine or lives inside of a fridge or something like this. Why might those things not use an Intel processor or an ARM processor? Go ahead. Well, certainly cost. I mean, okay, beyond cost. Yeah, exactly. So we don't need a fridge to be able to play Battlefield. Although I guarantee that at some point there will be a fridge that can. So, oh yes, we do.
If my fridge can't play you, it has no business in my kitchen.
Somebody brings their toaster into Milwaukee PC complaining that Fortnite keeps crashing. The thing just won't stay up on the toaster.
Can you go find
me? Why? All right, so, I mean, you're right. As he pointed out, I mean, when we talk about a fridge or a washing machine or something like that, these are not general purpose devices. These solve a very specific problem, right? And they need a microcontroller, they need a processor, but that processor only needs to have a collection of magic tricks sufficient for solving the problems that are on that system. Okay, and could you use a general purpose processor? Sure, but you'll be horribly underutilizing it. You'll be using more power than you need to use. You'll be spending a lot more money than you need to spend. So having specialized equipment for those types of things, having these little embedded processors, which do follow some standards. There are some small embedded processors that have a somewhat general purpose instruction set for washing machine-like devices. Okay, appliances, things like that. So that way you might have a similar chip that goes across multiple classifications of the devices, but they're still in kind of that appliance world. Now, one thing you might say, well, why might that be? If you have a chip that's somewhat general purpose, it's not going to play Battlefield, but it'll work across multiple appliances, and it might have some magic tricks on it that aren't necessary for a washing machine. Why might they use kind of a standard chip like that? Go ahead.
So they can kind of reuse some of their really base system code.
There could be a reusability factor. I think go ahead. There might be some truth to that too. I mean, they may be making that decision between the cost of the chip versus the cost of developing the software. And this kind of goes with what you were saying too, the cost of developing the software for 9 different devices. Okay, but there's really, I think, a main reason that's very compatible. I think those are both good reasons. I mean, those aren't wrong. But there's a connection I'm trying to make over to the software world that does exist in these embedded system worlds, and that's standards. So if you are somebody who's in the business of, you're in the engineering side of it, and you're in the business of repairing dishwashers or repairing refrigerators, things like that, chances are you don't want to have to learn 30 different instruction sets, right? For going to all these different devices. Like, okay, well, I'm looking at a 1997 Maytag, which uses instruction set X, Y, and Z. I mean, you're going to have to do that a little bit because these chips have evolved over the years. But in general, if we can have kind of an appliance class chip, which is low powered, low cost enough, let's say, where the skill set for working with it is a cross-trainable skill set across different appliances. There's advantages to that. And then you have to look at it at the economic level of, is it worth the money for, if you can buy these chips in gigantic bulk, take a company like Maytag or Whirlpool or something like that, that makes a lot of different kinds of appliances. Maybe they make up the cost difference that they would have had for these multiple chips by buying a whole bunch of that one kind of chip. Or at least maybe it's close enough that it's worthwhile to not have to have all sorts of specialists for servicing these devices. Kind of make sense? But the punchline maybe for us, because that starts getting into some of the economics of it. And at some point, somebody's going to make a decision based on money. But from our perspective, what we're looking at here is probably domain-specific architectures when we talk about embedded systems. So this is a fancy way of saying tiny computer in an appliance. In a appliance, right? Whatever. All right. These guys typically have smaller instruction sets. And I might throw in here, I just said it a minute ago, but domain specific. Smaller domain-specific instruction sets for solving the types of tasks that appliances need to solve. Okay, and you can take it away from appliances and put it into other kind of small things like that. You start dealing with like remote, controllers for, like scoreboards, stuff like that. Some of these things, scoreboards are relatively simple, but you start getting into kind of pretty high-end scoreboards like they have at like the Bucks Arena and stuff like that. This thing isn't just a simple controller that just turns numbers on and off. This thing is a programmable thing where they can put up pictures and have things running on it and all sorts of stuff. So those are going to have probably a classification of chip that is somewhat domain specific in that field or in a related field. So the idea is that we have processors around the world. We have lots and lots and lots of different kinds of processors are out there. Typically, when we think about a CPU, we're thinking about them in terms of Intel or AMD because those are our generic CPUs. Well, not generic, but our general purpose CPUs that are in all of our machines. And now we're going to start after this class. I think I asked this before. How many of you had heard of ARM processors before you came into this class? Okay, so just a couple of you. So the idea is that you've been carrying them around for years, right? You've had ARM processors inside of your cell phones for a long time now. Yet, I think we talked about with PowerPC chips, reduced instruction set processors died off a while ago because they really started to shine in low-powered battery-controlled devices. They didn't work out as well in the desktop computing world, mostly because compilers. Well, there was a production issue with it. We talked a little bit about how processors are made last time with like slicing silicon things and making the dies and that kind of stuff. The creation of RISC processors, whether it was the nature of RISC itself or the people who were creating the RISC processors, had a high failure rate where it just wasn't economical. But now it's what we use in our smartphones. So learning ARM is a useful skill. In fact, most new processors that come out, even in what we're considering our general purpose computing now, are ARM based. Okay, so let's see, what's the basically any new device that comes out that has a battery in it that is smaller than what you would consider a very portable laptop likely has an ARM processor in it. Okay, somewhere we have that crossover right now, where you have what's a small laptop versus what a phablet or something like that, or a tablet type thing. So iPads, for instance, have ARM processors in them, whereas most of your laptops are going to have Intel or AMD instruction set based processors in them. But we're moving more and more and more towards the ARM processors. We're going to hear a new instruction set, well, at least an improved instruction set come out from Apple tomorrow's event. I thought it was today originally, but apparently it's tomorrow. They're going to announce their whatever chipset, which is, they're going to say it's 30% faster than last year, or it's up to 60% faster than last year. So, what is it when they say that? We've talked about this already. What does that mean? When they say it's 60% faster than last year's chip, what are they likely talking about?
In one specific.
Go ahead.
Like at their highest one in specific, like the best.
For something very specific. Yeah, so there's probably some aspect of that chip that's been updated to solve a very specific problem, or a collection of very specific problems that are up to 60% faster if the moons align. But in general, the architecture is going to be compatible, certainly, because you don't want to have every app that you bought on your phone this past year not work on the new phone because it's a whole different architecture. So at the very least, it's going to be backwards compatible. But you're probably going to have, I'm just throwing a number out there, 98% similarity with a couple of optimizations in there, and they'll be able to point to one or two of those and say, these ones are a lot faster if you use them in this very specific way and that kind of stuff. So in any case, it'll be interesting to see what they come out with architecture-wise. So I encourage all of you to either, whether you watch it live tomorrow at noon, you shouldn't watch it live at noon tomorrow because noon to 1 tomorrow is Bible study. It's usually Tuesdays, but Bible study, you get free lunch tomorrow. So I'll be there at Bible study, and it's possible I might have my phone giving me a streaming update, but we should be paying attention to Pastor Smith. But in any case, from our perspective, we might be most interested in what's the architecture that gets announced. So we might spend some time on Thursday just talking about what was announced from an architecture perspective. Okay, but there's this whole world of embedded systems that live around us and all sorts of different things, especially with this idea. How many of you have seen this phrase before? IoT. Have you seen those letters next to each other before?
Yeah.
Okay, what does this stand for? Go ahead.
Internet of Things.
Internet of Things. And what does that mean? What does it mean for there to be an internet? Well, what's the internet? If you had to give a generic definition of the internet, what might you say?
Complex series of tubes.
Complex. You have the weirdest way of describing it. Well,
There was a congressman who
yeah, what was the thing?
The internet was a series of tubes.
Was it last year or 2 years ago? The parenthetical
Oh, yeah.
parenthetical notation.
Anyways, no, it's like big web of internet connected computers.
You can't use the word internet to define internet.
Application of software to communicate. Big web of interconnected.
Oh, interconnected. Interconnected. Okay. Yeah. So we have a whole bunch of computers that are connected to each other. Okay. I'm okay with that. Yeah. Big web of interconnected computers. And we happen to associate the internet with a whole bunch of specific applications. Web browsing, video streaming, things like that. We used to have some other applications. If we think of email, FTP, we probably don't think about FTP too much in terms of FTP anymore, but we still do file sharing and file transfer protocol. And it's still used today, which is usually hidden under a couple of layers of software that make it so that, I can drag and drop this guy here, and it's shared. It works. So in any case, so we think about the normal internet that we've dealt with for years. Well, now we have this thing called the Internet of Things. Okay, what's the Internet of Things for? What's the concept of that? Go ahead.
It's basically connecting a whole bunch of different devices we use together so they can share data and
get data from.
Okay. Yeah, so first of all, we look at the big T here. What is a thing? Well, it's a pretty broad word, right? There are lots of things. And one of the funny things with the Internet of Things has to do with some of the crazy things that we've decided to put on the Internet of Things. For instance, the funny thing, I think the funniest thing I've seen more recently is, and this isn't the first one, but there are toasters that are on the Internet of Things. The early ones weren't really on the Internet of Things because they weren't network connected. Instead, they had like a either a USB drive or an SD card or something like that where you can put a picture in there. It would burn that picture onto your toast. Right? I mean, who doesn't need Yoda toast? Well, now the Internet of Things ones, you could have a like a library in the cloud of pictures you might want to have on your toast or your waffle or something like that. And it can either randomly select it or brings up a thing where you can select, it's like, oh, I'm going to put Darth Vader or whatever. I'm going to put this picture of this thing on my toast. Now, you might say to yourself, well, why does one need that? Now, the Internet of Things toaster advocates would probably say, well, why don't you need that? Okay. So it's kind of funny when you think about it from a toaster perspective, but how many other things are now part of the Internet of Things? When anything, we're going to have toothbrushes on it. We're going to have, shoes. I mean, you already effectively have keychains because now you've seen several of these tracking type devices that you can like put in your keychains for when you like lose something. The early ones of those, use some different technology, but the new ones are using combinations of Wi-Fi, Bluetooth, cellular networks, near field stuff. So, I mean, these are full-fledged microcomputers that you're putting on your keychain. So this Internet of Things is more of a networking type of conversation, but from our perspective, many of these different devices will have embedded systems in them at some level, and we have to think about the architecture of those type things. I think maybe some of the early dives into before we started calling it IoT was like the automated lights in your house and stuff like that. I think I've mentioned in some of my other classes that we only have Philips Hue lights in my house. So for last Christmas, I think I've told you what it would do. Do you know what I got my wife for Christmas? I 3D printed it for her. A whole bunch of them. These little things that cover all the light switches in the house. So you don't use a light switch. Because if you turn the light switch off, then you've messed up your ability to use Alexa to turn lights on and off, or use your app to turn lights on and off. So for years, we had little Post-it notes over the light switches. How many of you feel that light switches are just too hard to use?
It's simple on and off. Well, it depends. Are they the kind that can fire a Nerf dart at and hit it on and hit it off?
They're not.
Oh.
No, we're talking normal. Yeah, it is too. They are too hard to use.
The door, you enter, you lay down on the bed.
Okay, now he makes a good point. There is an advantage to that. You're already in bed. You've left the basement light on. You don't have to get out of bed now. You can either open your app or yell across the room to Alexa and say, Alexa, turn off the basement light. And then Alexa may or may not hear you. And it turns it on brighter. And my wife, a lot of times she'll go to bed before I do. So she's in the bedroom and the lights are off. She turns them off, but the rest of the house is still on. So when I'm ready to go to bed, we have multiple Alexas around the house, and this is not my idea. This is all our whole house is like the smart house, and I just think it's a nuisance. But in any case, then you have to tell Alexa to turn off all the lights. You got to make sure you enunciate that way she doesn't turn on all the lights or something like that. But then I can't speak too loudly. If you haven't noticed, I can project. Okay? Because she's sleeping 30 feet away, right? So I'm like, Alexa, turn off all the lights. Sometimes she doesn't, I got to talk a little bit louder. And then we finally figured out how to turn the voice off, because what would happen initially is Alexa would go, Okay. And, and I actually think maybe originally Alexa did that at all her points across the house. Yeah. Yeah, so I could be like downstairs talking to the downstairs Alexa. You can actually, how many of you have multiple Alexas in your house? This isn't something that just everybody has?
I don't know.
I don't think I'll ever have one because I just don't feel comfortable having a list.
Oh, but it records everything you say. But if you want to go ultimate laziness, as long as you have enough Alexas, you can send a message. Let's say I'm downstairs in our bottom floor, and then my wife's up on the third floor, and I want to send her a message, and I'm too lazy to text. You can tell Alexa to send a message, and she'll repeat it in all the other Alexas around the house. So I'll say, Alexa, send a message. Can you bring me a glass of water? I mean, I'm maybe 10 feet from the fridge, but I mean, I'm comfortable. I figure she might be coming down soon anyways. A lot of times I'll phrase it like, when you come down, no rush. Can you get me water? It's the ultimate laziness. Just identify ways of using our technology.
That's like the one with the teleport where you can just teleport everywhere. It's don't be delay.
What's the minimum distance you would teleport?
A mile, maybe. I still really want like stations of pneumatic tubes, so I can just punch in something and it'll just get it from my pantry and.
So kind of like the banks.
Yeah, exactly. Like
But who's going to load it into the tube on the other end?
Some automated robot.
Or you can train a chipmunk.
Or that. Yeah.
They need jobs.
How can you even train a chipmunk?
I don't know. You probably figure out how to train a chipmunk. All right. So in any case, when we think about this Internet of Things, we have all these devices that are smart connected. Many of them are going to have embedded systems. Many of them might have an architecture that's going to be a very small architecture relative to our general purpose processors. Okay, so what we get out of this is not so much, we don't care so much about the Internet of Things in this class. We care more about this idea of embedded systems and specialized processors. But regardless, you're going to have a list of magic tricks that that processor has. So when we think about an architecture, we've said this over and over again. We think about the instruction set, but now there's some new things that we're going to be concerned about or have to know about. So available registers. Okay, and that's going to come in the form of total number of registers, the size of the registers, and the names of those registers. Because we're going to have to refer to them, and we'll see that here in a minute when we look at some example things. Okay, so available registers. Cache configuration. So do we have any extra cache on the processor? So kind of slower memory than registers, but faster memory than your system memory. You start getting the low cost processors, they are either going to have no cache or extremely small cache just for a little bit of optimization, but that's taking into consideration that we're solving much simpler types of problems on them because cache is expensive. All right. But these are some things that we start expanding on what we need to know if we're writing some instructions or writing a program in assembly for a particular processor. We need to know what are the magic tricks, what are the registers I have available to me, and what are their sizes, because those guys are going to be used in terms of those magic tricks. All right. And then maybe some additional memory stuff. But those first two are kind of the big ones. Cache costs a lot of cash. That's right. Okay, where's my... Okay, they call it the leg V8 assembly language. Whatever. Okay, so they're showing an example of an instruction here, and I'm pretty sure this is the destination. These are the two we're adding together. Okay, so they're saying add B and C together, storing the result in A. So giving an example of this, these aren't the actual names of registers. They're just showing kind of the makeup of what an instruction looks like. So we can think of this as like the add function. Okay, and the add function takes 3 parameters. It takes in a destination, it takes in a source 1, and it takes in a source 2. And what it does is it grabs the value from those 2 places, whatever that means, and we'll talk about how those values get placed into places, and adds them together and stores the result back in this first parameter. Does that make sense? Now, this is one of the patterns that you, right off the bat, if you've had any Intel assembly, is a little bit different. The add instruction in Intel assembly only takes 2 parameters. Okay, it takes your destination, which also acts as your first source, and then it takes your second source. It adds them together, stores the result, overwriting your first source. Does that make sense? So that doesn't make it necessarily better or worse. It's just a constraint you have to work with, that you know you're going to destroy the value in your original source when you use that add instruction. Where with ARM, you do not change the values of B and C, your 2 sources here. The result will be put in A. Make some sense? All right, so that's just a generic instruction. Then they want you to write some instructions that are like this. So this will be add Z, comma, X, comma, Y, so on and so forth. All right, so let's get down to where it starts talking about specific registers. Notice we also have a sub command for subtraction. So this subtracts, I think it'll be C minus B, storing it in T. I don't think it's B minus C. I think it's C minus B. Almost positive. Yeah, A minus E, storing the result back in D. All right, so that's just getting you used to using these instructions in general. These are not the names of registers. These are just made up variable names just for testing purposes. All right, but that's the nature of an instruction. And we can think of them as a collection of functions. It's the function name and then the parameters. Okay, and parameters, there are instructions that only have 1 parameter. Actually, there's instructions that have 0 parameters to like exit a program, but a majority of our instructions will have at least 2 parameters, if not more. So they're showing for this initial adding and subtracting stuff, mathy stuff. We have destination, source 1, source 2. Okay. All right, so now here we get down to our register stuff. So we have 32 registers. We have X0 through X30. And then we have this extra register, which is for, this is a 0 flag register. And this guy always gives us the value 0. So if you need to work with 0, he's kind of a quick and easy way of getting a 0. We're also going to have a collection of flags that we'll see later where certain things get set. So we can do some mathy stuff, and then we can check the flags and see, did anything weird happen there? So for instance, like an overflow. If you have an 8-bit value, what's the largest number that can be stored in an 8-bit register? It's the biggest value that can fit in an 8-bit register. That is a register that can hold 8 bits of data. 255. So the largest value, this is now, in that case, we're treating it as a unsigned value, right? Okay, so we're using all 8 bits for magnitude. And we're going to say the biggest value, 8 ones next to each other, is 255. So if you try to put 256 in there, what do you end up with? Well, an overflow. In software, it's typically an overflow exception. In hardware, usually the way you would end up adding it, you would end up having a 0 in there because it would overflow. And then you'd have a flag that gets set that you would check afterwards and say, did everything go okay? And if you see the overflow set, you know that, oh, my last operation set the overflow. That means I can't necessarily trust that number, the number that's in there. It's too big. And that's where you might have an exception or something like that. All right. But this is where, it becomes real. When we think about writing software, when not very often in your programming life so far have you probably run out of space in an int. If you did, it was likely a bug. You know, you had some infinite loop or something like that where all of a sudden an integer wasn't big enough. Or you had you were just working with a giant number. Well, what happens if you get too big on a int? So let's use a byte as an example. So if I have a byte data type in Java or C++ or C, whatever it is, they're all the same. That is an 8-bit signed value. So that can hold the values of negative 128 to positive 127, right? And we're going to talk about 2's complement in here at some point, which tells us how it's actually storing those negative numbers. So don't worry about that right now. But what happens if I have in a byte the number 127 and I add 1 to it?
It'd just be 0 there.
Am I going to get an error? So if I have 127 in a byte, let me show you. Just do it in here real quick. So I'll say byte B is equal to, here, we'll start off as 120. And then I'll write a for loop. Let's do 10 times. So the first time through, this is going to print out 120, then 121, then 122, 123, up to 127. Then it's going to add 1 to 127, which gives us 128, which does not fit inside of a byte. So what's going to happen? Is this going to crash? Did you type it in?
No.
Okay. Yep. It'll wrap back around, and that actually has to do with how 2's complement works. It's not wrapping back around because that's just what it does. It's wrapping back around because of the way negative numbers are stored and because of the way addition works. It's doing that addition at the binary level. And when you add 1 to something and you ultimately get the overflow, you'll end up with a 1 followed by a whole bunch of zeros, which actually is equal to negative 128 in encoded negative numbers, which will make sense when we go and talk about that. I'll go ahead and run this real quick. And you see we have 120 through 127, then it went to negative 128 to negative 127. So I actually saw it wrap around. Okay, so that means that I actually could have an infinite loop here. So if I just throw a whole bunch of zeros in there, we're going to see it's just going to keep adding and keep spinning back through. So even though a byte can only hold 256 unique values, I'm going through way more than that, and it's just circling around over and over and over again because it's doing the binary rollover. Does that make sense? What's happening under the hood? And we'll see how 2's complement actually works at some point, and it'll make sense why it's working this way. This isn't like some special Java thing where it's saying, oh, well, you're trying to put 128 in a byte, so we'll just jump to the smallest value. No, it's actually working out at the binary level. All right, so in our ARM architecture here, we're going to have 31 registers of various sizes that we'll look at. Okay, we're going to have some 8-bit, we'll have some 16-bit, we'll have some 32-bit and 64-bit registers, but we have a whole bunch of really fast hardware-based variables. It's what we care about the most. Okay, because chances are for stuff that we're going to write, we're not going to use that many of these registers at once. But you can imagine if you have a compiler that, you have a pretty, complex high-level program, and that compiler is turning it into the low-level assembly code for ARM, let's say, or in this case, LEG, it might need to work with many of those registers so that it doesn't overwrite variables. Right? If you think of each register as being capable of holding one of your numbers, let's say you might have an app that's having to keep track of 25 numbers. That's not a ridiculous amount of numbers, right? 25 numbers, that's not ridiculous. So if you just think about it at the very basic level, if I have to hold 25 numbers inside of registers, I only have a handful of numbers left. that I can use my registers for. Now, the reality is they don't store them all in registers. We could also work with arrays. And then we'll start talking about how base addresses work. So when we first talked about arrays in the programming class, we talked about base addresses and things being offsets from those base addresses. Same thing works here. We could store the base address of an array inside of a register, and then the actual values will live in system memory. A little bit slower, but also then frees up our super fast array or super fast registers for other things. All right, that makes sense. So we really have two pieces here. Okay, we have 32 total registers, fast memory, variables built in hardware, and then we have 2 to the 62nd memory double words. So we could think of this like memory, but this is actually on the chip, so it's faster. We can almost think of it like cache. So accessed only by data transfer instructions, uses byte addresses, so sequential double words addresses differ by 8. We can kind of think of that almost like an array. We can have a base value and then an offset from that base value, and that'll make sense when we look at it. Memory holds data structures, arrays, spillover from registers, things like that. All right, so you can think of this 2 to the 62nd power for memory, which is a really strange thing. I wonder, they're probably using one of those guys to manage what memory is currently being used. But regardless, we have two elements here when we talk about this architecture. We have hardware variables, and then we have memory. Okay, and these two things working together allows us to solve our problems. All right, so let's get that into a slide. So this kind of goes along with available registers and this cache configuration. So we can think of this guy as our hardware variables. And we have 31 of these guys, specific hardware variables in ARM. And then 1 0 constant. And then for our cache configuration, this is our onboard memory. This is 2 to the 62nd power, which is a really strange number. So that is going to be 19.2 quintillion divided by 2. So I guess 9.1 quintillion. Because 2 to the 63rd is what you would typically, you'd have plus or minus 2 to the 63rd for a 64-bit signed value, which is 19 point something quintillion. So divide that in half, you're at 9.6 quintillion. Big number. A big number. And then you're going to divide that by 8, and that's going to give you the number of buckets that you have, because each of them says it's addressed in 8 bucket jumps. All right. But in any case, this is onboard memory. So we have registers, and then we have more storage space that's going to be slower than registers, but still fast. All right. We're going to see these two things, how they work together. All right. So for example, you might add 2 values from memory storing the result inside of a register. Or you might load into one register a value from memory, and you might load into another value a value from memory. Then you might add those 2 registers together, storing the result in another register. See, there's this play back and forth between using registers for doing things and then having things that are a little bit more long-term storage sitting in your onboard memory. Make some sense? At least in at the high level. Okay. All right, so here are some instructions. So we have our add and our subtract. So notice add and subtract. This guy takes in So first of all, these are names of registers. So if you noticed up here, when it said our registers, we have X0 through X30. So in ARM, the names of those hardware variables is X0, X1, X2, X3. That's how we reference those registers. All right. So when we're writing our code, we can think of them like variables. You know, some value is stored in X0. Some value is stored in X8. But under the hood, X0 and X8 are actually pointers to a physical hardware thing. All right, which is fast. So we're not resolving a variable name. We are jumping to the data path where that guy lives and grabbing its value. So it's very, very fast. All right, so when we look through some of these things, we have a couple of versions of add. So our first two versions take all three parameters are registers. So this is add this register plus this register, storing the result in this register. Similarly, this one works the same way except it's subtraction. Now, add I, this is add immediate, and an immediate value is a literal value. So let's get that in a slide. Immediate values. These are literal values. Now, we've heard literal values before, but it's kind of a fancy way of saying a number. Okay. And in programming languages, you might say a number or a value-driven keyword, like true or false. Those would be literals. True is a Boolean literal. False is a Boolean literal. 0 through 9 are int literals. Any number, any numeric value is a numeric literal. Technically, we can call chars, call it a char literal, but it does require a mapping on Unicode or from ASCII, depending on what what vintage language you're working with. But they would typically be called literals. But these are values that exist. We can't, and they can't be changed. So these are permanent values. For instance, we can't decide that the number 5 now means something else. 5 is 5. Go ahead.
So do assembly languages tend to have keywords like true or false? Specifically those. I don't understand.
No, because they have these things called jump instructions that jump typically based on a flag being set. So they have the equivalent of it, but not a specific keyword.
Okay.
Yeah, generally speaking, if you question whether something is in assembly language, you have to ask yourself, would it fit in a bit space? So can it be represented as zeros and ones? So true, the way C did it was literally as the integer value, zeros and ones. In assembly, we get the efficiency of being able to treat it as a bit value of zeros and ones. That's where a flag comes in, because you can actually get multiple flags. So if we have an 8-bit value and you only need to know whether something happened or didn't happen, you could actually get 8 flags fit inside of a single 8-bit register. You just say bit 0 is this flag, bit 1 is this flag, bit 2 is this flag, something like that. So a lot of times an if statement might say, if some flag is set to 1, then do this. Something like that. So the concept of Boolean exists, but it's operating off of a single bit. Okay. All right, so we have some versions of add that take immediate values. So this is going to add the content of X2. X2 is a register to this immediate value. So we're adding 20 to that, storing the result back in a register. So this allows us to work with literal values. But notice only one of these guys could be a literal. I'm 99% positive that add immediate requires this guy definitely has to be a register. I believe this guy also has to be a register. You just are given the ability to have a single immediate value. So this is kind of like doing like adding 1. If you want to add 1 to a value, you could say add I x1 comma x2 comma 1, and then your next instruction could be move the value from x1 into x2, overwriting x2 with its cloak. You might be able to say add I x2 x2 1 and do that all in one instruction. I think you could. I think the destination and your source could be the same. I think that's allowed. So you could increment x2 by saying add I x2 comma x2 comma 1. That would increment it by 1. Okay, so these are the add and set flags. So we talked about this idea of flags before. So this allows certain things to get set. We'll see some examples of that. But this ultimately is doing the same math, but also says, I plan on checking consequences of that math. So if you have an 8-bit value, if your destination register is 8 bits, and just to keep it simple, let's say we're only holding unsigned numbers. So the biggest value that can fit in there is 255. And my source register is 200, and my destination register is 200. My sum would be 400. 400 will not fit in something that's capable of holding 255. So even though both of my source registers could hold the value, they were less than 255, once I added them together and tried to store the result back into my destination register, it overflowed it. Now, if I just do a add or sub, I'll be left with a value in my destination register. It'll be the best it can after it loads it in their binary style. So I'll be missing portions of the value. So it won't be an accurate number that I can read from. But it won't set any flags, so I won't be able to go and check and see, did something bad happen? Did something bad happen? Does that make sense? So something you need to be careful of. If you're writing some code that could have an overflow, where you try to put something in the destination register that was just too big, then you can go and check. You can do the one that sets flags with the intention of then on your very next line checking those flags with a conditional and saying, did something trip? If something tripped, I need to go deal with it, or that maybe tells me that the value is too large or whatever. It says you're interested in that. All right, and then here is the combo meal. Okay, so this is the add immediate and set flags, so you get the more bang for your buck. You're allowed to use literal values, and it also is going to set flags for you. All right, so now these last ones. So these are our arithmetic operators they're telling us. So this is mathy stuff, adds and subtracts. They come in a couple of flavors. Okay. Now these next ones, these are data transfer. How do we get data to and from registers? Okay. So right off the bat here, we want to load register. So we are going to load into X1. Now, this guy right here, this is how we reference the onboard memory. So this says the value we're going to load into X1 is go to the base address that's stored inside of my register X2 and then walk an offset of 40 from that base address. And whatever value lives there is the one we're going to store in X1. All right, so obviously trivial stuff, right? How many of you are it's floating up here somewhere? Let's look at an example here. Drop my pictures.
What the hell do you want stand for?
It's load. Is it unsigned register? I'm not sure what the wording of it means. So the LD is load. The R is register. I'm not sure what the U stands for in there.
It might be unsigned because later you have a load sign.
Oh, load signed, yeah. So load unsigned register. Yeah, let's go with that. All right, so I'm going to create something that hopefully looks familiar for some of us, where we've had arrays in the past. So, and I've kind of mentioned before, whether it's in this class or other classes, kind of the way memory works is, and well, when we create an array, and I say that arrays must live in contiguous memory. What do I mean by that?
Not volatile memory.
Let's try again. What does contiguous mean? One after another. So contiguous memory says, I need a chunk of memory where all the values will live right next to each other in memory. Okay? Why is that important for arrays? Okay? Arrays are fast. Why does that make it fast?
It doesn't have to like go and check for the next one. It's for the memory.
Okay, what would the example be that it would have to go and check for the next one? Well, let's go this route. If I have an array, how do I get to bucket 5 of that array?
You move 5 plus 5 times 4.
Okay, so the array itself holds the base address of where that array lives in memory. Holds the beginning of it. If I want to go to bucket 5, I walk an offset of 5. Was that five jumps? Let's assume it was 5. It was 5 jumps. Okay, I move an offset of 5 from that base address, and now I'm at my value. Okay, I can only do that if all my values are right next to each other. Okay, if bucket 0 is here and bucket 2 is here and bucket 3 is over here, like in a linked list, I can't just walk through memory like that. Okay, and what's nice about that is I didn't actually have to go from bucket 0 to bucket 1 to bucket 2 to bucket 3. I just went to the base address, calculated where bucket 5 would be in memory, and went there. So it allows me to quickly get to a particular value because of how arrays work in memory. They live in contiguous memory, they live right next to each other. Memory works this way as well. Okay, so when you have these crazy looking hexadecimal memory addresses that go up to these giant values right off the bat, we're intimidated because it's hexadecimal and that looks scary. But the reality is the way our computer's memory works is far, far simpler than the way addresses work in real life, right? In our computer, everything just lives in one gigantic street. Okay, oh, you're in house 22,638,000,000 flat. Let's just stop there. It's just got a great number. Okay, that's the house you live in. You just run down the street to that, right? And if you know things are stored contiguously, you could just start at the base address of memory and then jump 2 point whatever billion I said it was down the street. And I'm there. Okay, because it was contiguous. In real life, when we talk about addresses, our addresses are complicated, right? We have a street address. So we have a street, we have a house number on that street. Some of you have apartment numbers within that house. Okay, if you're in an apartment building. Okay, and then all of that only makes sense if you also have the city and the state. Because there's multiple cities with the same name in different states. I bet you there's probably a state that has more than one city with the same name. It's got to exist.
Berlin in Wisconsin.
There's 2 Berlin, Wisconsins?
Yes.
But they do have different zip codes. At least I hope that's the case. Because then I would assume mail never gets delivered or always gets delivered. One of the two. It's one of those 2 things happens. Okay, so I'm showing you an example here. Let's just go with 4 buckets like this. So we're going to say that this guy, I'm going to put some dudes here. So this is going to be memory addresses. So I'm going to say this is memory address 100. This is 108. This is 116. And this is 124. All right, and I'll put some values in here. So this is going to be a 4. This will be a 7. This will be that's a 79, I guess. This is a 2. And this is a 86. Okay. So now we're going to go ahead and give ourselves a register here that's going to be hold 100. And we're going to name this guy X1. Okay, so we're going to name this guy X1. And then we're going to have an instruction that's going to say load UR, and we'll load into X2 the value X1, comma 2. Okay. Oh. We'll write this in array format here. So this is bucket 0. This is bucket 1. This is bucket 2. This is bucket 3. All right, we can probably make those different colors, but whatever. Okay, so these are the memory addresses. These are the corresponding bucket numbers. If we think about them like arrays, here's the values that live in there. Here's a register. This is a hardware register that just happens to hold the value 100 for no good reason, seemingly until we see it used in a load instruction. So I'm going to load into X2. So we have this other register floating out here. X2, which we'll say currently has nothing in it. We're going to load into the destination X2, and we're going to load into that guy the memory. This is the value that lives at a memory address. What memory address? Whatever address is in X1, so the base address of X1, which is 100, plus 2. So this will get us to memory address 116, which is going to give us a 2. Like that. Now, it's either like that or the plus 40. I think it's the way I just said it. But this plus 2 thing could mean, give me the value from memory address 102 instead of 2 jumps off of 100. But it's still an offset thing. We'll see when we see a real example, we'll clarify. But this is the way it works. This says go to the base address X1, which holds 100. So I'm going to go to memory address 100, which is right here. And then I want to take 2 steps from there. I'm suggesting it's 2 byte-sized steps. It might be 2 bit-sized steps. Okay, but I'm suggesting it's 2 byte-sized steps. That's how arrays work. So we're going to take 1 step, which gets us here, 2 steps, which gets us here. The value that lives there is our 2. That's what we're storing inside of X2. Does that make sense? That's how that offset thing works. So it works the same way arrays work. We're just seeing it inside of our this is the relationship between our registers and our onboard memory. So we can have stuff stored between the two. So quickly here, we see we have ways of loading a register, ways of storing in a register. We'll look at these more next time. So all sorts of stuff we can do here. Here's our logical operators for ands and ors, exclusive ors, all this stuff. Here's conditional branches for if statements. And then here's jumps where we can use these for loops. So memory. How do human beings solve problems? We remember stuff. Here's memory stuff. We ask questions, logical conditional branches. And we use repetition. That's our jumps. Exact same stuff represented in a low-level instruction set. All right, makes sense? All right, so for next class, let's read and do the, let's do 2.1 and 2.2. Just do all the, the interactive exercises and stuff like that. So get through 2.2, which we've gotten through half of that already. Just do the practice stuff along the way. Threat of quiz on Thursday related to that. Sound good? All right, I'll have the Bible homework up today. It'll be due on Sunday at midnight. I should have the grades from your other work up by probably late tomorrow morning. But in any case, I will see everybody on Thursday.